Hi, my name is Bhakthi Liyanage. This is the final presentation for Data 670 Data Analytics Practicum. Today I'm going to talk about predicting weather-related flight delays based on weather data. Before we go into my model creation and the whole process, I will briefly give you a brief update on the problem and about the data. So the business background, the Skyline Business Travel provides concierge service for business travelers. So the objective of the problem the problem is increasing the competitive edge by providing value-added services to corporate customers. So how do we achieve this objective? The solution is identifying the impact of weather-related delays affecting their customers' travel plans. The company is investigating ways to improve the flight booking experience more streamlined and customer centric by including data driven decision making. Let's talk about project deliverables. So the project deliverables are twofold. The first one is developing a machine learning model using the algorithms that we learned over the course and try to find the best model to predict weather-related data based on weather data and predict whether a flight is going to be delayed or not at the departure airport and the arrival airport. The second aspect of the project deliverables is that operationalizing the model. So we need to deploy the model into web application so that the clients can choose their origin and destination airport, the time, the day of travel, and so on, and the system will predict whether there is a chance of flights being delayed or not. The dataset description. I have three datasets. The first one is the flight delays with airport codes, which has about 2.7 million observations with 20 attributes that are collected from 1st of April 2013 to 31st of October 2013. So this gives all the statistics of the airports and any weather related data around that airport. And the second one is weather readings at airport locations, and the third one is the geographical data around the airport codes. That data table will serve as a lookup table for the fact tables. Let's investigate the predictors and targets. So in initial dataset, I have 25 predictors including year, month, day of month, and the time of the flight, the carrier, original airport, departure time, and so on, along with all the weather related data for destination and origin airport. So my targets would be to determine whether flight will be delayed for 15 minutes or whether a flight will be arrival will be 15 minutes delay or not. And also I will also be trying to predict whether a flight is going to be cancelled or not. In terms of tools, I'm using DashDB because I have about 2.7 million records in one of the data table, and it's very hard for me to use my desktop resources to process that much of data. So I'm using DashDB or DB2 on IBM Warehouse, which is a cloud-based database to do my initial data preparation. And also I'm using IBM Watson to get some insights into the database, quick insights which gives me a really nice visualization. For my model creation, I'm using R and SAS Enterprise Miner. SAS Enterprise Miner has some uh, models that are not available in R, so I'll be using R models and SAS combined to create some of the models. So my data execution plan is like this. I'm going to be using a um, supervised learning model. So according to supervised learning, we will be providing raw data along with labels, and we will be doing some data exploration where we explore the data, identify patterns, high-level patterns, and also we will be doing some data preparation in this step. And also we will be looking for any features that are most influential on the model. So if we decide that some certain features are not influential, then we will be removing them. We will create the feature matrix, and then we'll feed the features along with algorithms into a model which will be trained based on the data. And once the models are developed, so we will be using multiple models, and then we will compare the models, pick the best model, and then we will operationalize that. Once we go into the operations mode, the new data will be fed into the new the selected model, and then the model will provide us the label. Quick data exploration. So initially I thought this the most influential predictors would be weather related. My hypothesis was that weather causes the delays, arrival delays or departure delays. But I was proved wrong when I fed the data into IBM Watson, and according to IBM Watson, it looks like that arrival delays and departure delays are mostly influenced by the airports and also carriers. So according to the left side image, we see that Chicago O'Hare and Atlanta Hartsfield Jackson, and also Newark LaGuardia, Newark Denver International and Dallas Fort Worth cause a lot of delays as well as departure delays. And also on the right hand side, it indicates that the delays are influenced by carrier as well. So for example, WN, which denotes the Southwest Airlines, has a lot of departure delays and airport delays. And also when you can see United Airlines, American Airlines also have a significant effect on departure delays and arrival delays. So once we identify do the quick data exploration, we will be doing some data pre-processing. So this project involves multiple data pre-processing processing techniques. The first one is normalizing or centering data. That means subtract the mean of the predictors data from predictor values. And the second data preparation is the scaling, which divides the mean of the predictors data by standard deviation. And the third one is the conversion. So I found it that if we convert the data into sparse metrics, the training would be very fast. So I converted the 29 predictors into a sparse matrix using one hot encoding. In terms of machine learning algorithms, I have selected three categories. decision tree-based models, logistic regression, and some ensemble models, which are bagging and boosting. I trained 7 models. So the objectives of the training and a whole exercise is to choose the model with which provides the minimum false positives and false negatives. And the second objective is to maximize the ROC and area under the curve. The third objective is achieve relatively high accuracy. So this table here shows 7 models, and the first column shows the accuracy, and I also take kappa value, sensitivity and specificity into account when selecting the best model. And also I calculate the area under the curve, true negatives, false positives, true positives, and also I created another column to denote the false positives and false negatives. That's what we are actually focusing on. If we can find a model which minimizes the false positives and false negatives, that would be the best model. And also right hand side I have plotted the ROC comparison for all 7 models, and clearly we can see that GBM, gradient boosting model, and extreme gradient boosting has the highest AUC and also the highest ROC. So that gives us some indication that XGB and the gradient boosting models perform better on this data set. One note that I have to mention that I have used R-caret package to create all the models, and also I have not, at this point I have not done the hyperparameter tuning, which means I have not optimized each model with its own parameter tuning. I provided tenfold samples, and using the same sample set ran the default models without any parameter tuning. So clearly we can see the total of false positive and false negative for GBM and XGB are less than the others, and also the false positive and false negative separately are lower in the GBM and XGB. And also if you pay attention to the accuracy also higher than the rest of the models. So we have winners, GBM and XGBM in this case. So I'll be using these 2 models for my prediction web application. The lessons learned. My initial hypothesis was that weather has severe impact on flight delays. However, after data exploration, it was provided to be otherwise. My hypothesis was false. Time of the day was identified as the most influential predictor, not any weather-related predictors. And also, I was surprised to see that a month of travel was also found to be an influential predictor. One other finding that I noticed that with this whole exercise was that tree-based algorithms provide more accurate results for binomial targets. Few other things I learned along the way was distributed processing. My dataset had 2.7 million records, and when I converted the data frame into sparse matrix, it became very large with 90 columns instead of original 29 columns. So I decided to use parallel distributed processing using some of the R packages supports parallel processing like do snow, which reduce the training cycle significantly. One other thing that I learned from this exercise was data pre-processing. When I fed the data as it is, it took so long to create the models, and also the accuracy and the performance was very low. But when I transformed the data using centering and creating sparse matrices, the training cycle was shortened, and also the performance was very high. The accuracy went up. So I think that was one of the major lessons that I learned, the scaling and centering of data. Finally, my next step would be to tune the hyperparameters for GBM and XGBM models to pick the best one out of two, and that model will be deployed into a web application using Shiny Web Apps. Thank you very much.